All right, welcome. Hopefully you can hear me. This is the topic 2.1, deductive reasoning, and I want to hide that because I don't want you to see the answers. I want you to try that by yourself. So what we're gonna do to warm up is we're gonna do this little, this is called sudoku. And just to get your mind working a little bit, you can probably see, shoot, I want you to see the answers for that. You wanna fill in the squares over here, and I already did that, I should have done that. But basically each row has to add up to, each row has to have 1 through 6, each column has to have 1 through 6, and each bolded box have to have 1 through 6, and there can't be any overlaps. Those are the rules, so you gotta make the numbers 1 through 6 fit in there. So pause the video and do your best. All right, unpause. And did you do it? Did you fill them all out? Well, here's the answer. I know this is kind of a bummer that I'm not here for this because we'd be doing this as a class. But there you go, as you can see, you have 1 through 6, 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 1 through 6. You have 1 through 6 in each column. You have 1 through 6 in each row. All right, so that was the puzzle. I think that's the unique solution. There's no other solution to that. All right, next, what I want you to do is to number each statement so that the scenario follows a logical order. All right, so go for it. Read through each 5. Read through each 5 and then see if you can number which one had to happen first, and then second, and then which happened third, and then which happened fourth, and which happened fifth. Pause the video and do it. And back. All right, here you go, welcome back. So this is just a logical thinking exercise just to get our brains going. Hopefully you started and put on some perfume. Dan's allergic to perfume and sneezed. Dan sneezed caused Jan to jump. Jan jumped, spilled the milk. Jan the cat ran to slurp the milk. All right, next one. So what we are doing in this class is we're developing a system of mathematics. The system we are developing is called Euclidean Geometry. It was kind of built, story goes, by this guy named Euclid about 2,300 years ago. And it's a system of mathematics that works on a flat plane, works on flat planes, and was built using deductive reasoning. Now, deductive reasoning is using facts to make new facts. And kind of a bummer we're not here. If I was here, I'd click on this link, and you can do that if you're online. You look at the videos, but it's just a little video. It's fine. But deductive reasoning is using facts to make new facts. And we've already done this in geometry a little bit, where we've defined words, and then we use those words to make new words, and we use those words to make new words. And that's kind of what deductive reasoning is. You prove something or you accept something, and then you can use that truth to prove something new. And then you can use that truth to prove something new. And that's called deductive reasoning. But you have to use deductive reasoning, you have to base it off of facts. So here's, for example, this is an example of using facts to make new truths. So for example, all musical, I think I skipped this, postulate. A postulate is a statement that is accepted without proof. We also call these axioms. Okay, so at the beginning of truth are these things that you just have to accept, believe it or not. Okay, all truth is based off of accepted truths. They're called postulates. And they may or may not be true, but we are accepting them regardless of if they're true or not. We're accepting them as truth. And then when we accept them, we can build on those things. So postulates are like the foundation. So here's some examples. I could state 1, 2, 3, 4. There's 6 postulates here, for example. So for example, and we're gonna call these facts. All right, so these are facts. So it's a fact that Jake plays the tuba. It's a fact that Lisa plays the trumpet. It's a fact that Kayla is a sophomore. Based off of these facts, can you determine if these are true or false? Or can you determine if you cannot determine them? Boy, that's a mouthful, right? So for example, can we determine that Lisa is a sophomore from these facts? Lisa plays the trumpet, and all of the trumpet players are sophomores. So can we determine that Lisa is a sophomore? I would say so. Lisa plays the trumpet, and all trumpet players are sophomores. Kind of how I did. Lisa for L, trumpet for T, sophomores for S. It's kind of how my mind kind of works there. So I was able to come up with this new truth. It is okay to say that Lisa is a sophomore based off of this postulate and this postulate. I was able to put those together. And that's reasoning, that's deductive reasoning. I'm using these facts to make a new fact. So now this is a new fact. Lisa is a sophomore. What about Jake is a sophomore? Can we decide that Jake is a sophomore? Well, let's see. Jake plays the tuba. And anything about tuba, anything else about tuba in here that we can connect? Let's see here, we can maybe, all musical instrument players are in the school band. Okay, so a tuba is an instrument. Okay, so Jake plays the tuba. A tuba is an instrument. And all tuba players are in the band. So we could conclude that Jake is in the band. Can we conclude that Jake is a sophomore? I don't think we can make that connection. So that is, cannot be determined. Okay. Can we determine that Kayla plays the flute? All right, let's try and do that one. Okay, Kayla plays the flute. Kayla is a sophomore. And what else did we say about sophomores? None of the flute players are sophomores. But Kayla is a sophomore. But it says here that a sophomore, a flute player is not a sophomore, but Kayla is a sophomore. So that's, we cannot connect Kayla to the flute in that scenario. Kayla's a sophomore. Sophomores do not play flutes. Okay, so that one is actually false. That's a false statement. And would you be able to, if somebody gave you these facts and somebody said Kayla plays the flute, would you be able to find the contradiction in those? That's kind of what you have to do. For the rest of these, I'd like you just to do what you can. So pause the video and try your best. Only one of these can be determined. The rest, there's no connection. All right, now you're back, you paused it, here we go. From my understanding, this is the only one that you can conclude. Kayla and Lisa are in the same grade. Well, Kayla is a sophomore, and Lisa plays the trumpet, and all the trumpet players are sophomores. So that means that Kayla and Lisa are both sophomores, so they're in the same grade. That's good. All the other ones cannot be determined. All right, on to our first proof here. This is what a proof looks like. And so what I'm going to do for a proof is I'm going to set forth some postulates. Now, based off of the postulates, I can make conclusions. So here's what we're going to do. We're going to say, given these postulates, we're going to prove that girls are evil. Okay? So here's the postulates. Postulate 1, money is the root of all evil. You've heard of that before? Money is the root of all evil, so we can write that like this. Money is the root of evil. See that? Money is the root of evil. Postulate 2, time is money. Time is money. And then postulate 3, you ever heard of that? Time is money. Postulate 3, girls require time and money. So girls equal time and money. Time and money. Now, let's take that over here. Let's start and see what we can put together here. So if we start with this postulate, postulate 3, we have that girls equal time and money. And then we can also bring in postulate 2, which says time equals money. Now, these can be combined. What can we replace this T with right here? It's like you have girls equal time and money. What could I erase the T and put in its place? T equals M. Oh, it's the end of the day. Here you go. And so we can take these two facts and make a new fact. That girls equal money and money. Okay, we just substituted. That was a substitution property. We substituted time for money. All right. Then it's known that if you do money times money, that's money squared. So we're substituting m times m for m squared, like that. Now, let's bring in postulate 1. So we're bringing postulate 1 into a proof. So this is a truth, this is a truth, this is a truth, and this is a truth. Okay. And it's also true that to get rid of a square root, you can square both sides. So we get to this. And now these two things we can combine together. So girls equal money squared, and money squared equals evil. And so if girls equal money squared and money squared equals evil, then that means girls equal evil. We did it. We made the connection. We were able to connect girls to evil. And so therefore, we now have a new theorem. A theorem is something that has been proven. Okay, so postulates are accepted truths, and a theorem is something that has been proven. So therefore, our theorem is our girls are evil. That's a new fact. It's a fact based off of these facts. Now, here's the deal about proof. Proof is only true if you accept the postulates as true. So ladies, if you think I'm being a little harsh, if you don't accept these postulates as true, then this theorem is not true for you. This theorem is only true based off of these postulates. Okay? So don't get upset with me. All right, back to geometry. So now what we're going to do is we're going to do the same thing with geometry. We're going to build geometry that same way. We're going to lay some postulates, and then we're going to use those postulates to make new truths. 300 BC, Euclid, a Greek mathematician, laid the foundation of math and formal reasoning by stating the first postulate of the first geometry textbook called the Elements. And if you click there, if you're online, it'll show you a picture of the oldest remnant of the Elements. It's not the original, but it's the oldest we have. Here's a little quote. Let me read it to you because it's so special. The Elements of Euclid not only was the earliest major Greek mathematical work to come down to us, but also the most influential textbook of all time. The first printed version of the Elements appeared in 1482. That's the first printed version. Now, again, it was written 300 BC, but then the printing press wasn't around until then. One of the very earliest of mathematical books to be set in type. It was one of the earliest books to be set in type. It's amazing. It has been estimated that since at least 1,000 editions have been published. Our geometry book, what our notes are based off of, is one of those editions. Perhaps no book other than the Bible can boast so many editions, and certainly no mathematical work has had an influence comparable to that of Euclid's Elements. All right. To this day, we still start our geometry with the same postulate that we used 300 BC, and that is postulate 1. Through any 2 points, there exists exactly one line. So if I make 2 points, I get one line, and we're accepting that as truth. However, you have to understand, it may seem obvious that if you have 2 points, you have a line. But what if we're on a globe? Okay, the North Pole and the South Pole. These are 2 points on a globe. Now I can connect these points many different ways, right? So there's an example by accepting this as truth, by accepting that there's only one line, then that takes us off of a curved surface. We are now stuck on a flat surface. We're on a flat plane. Postulate 2, a line contains at least 2 points. Now, these are connected, these postulates are connected because they are converses. This says 2 points imply a line, and this one says a line implies 2 points. So those are converses of each other. If you remember converse, like the switch and the if and the then. Postulate 2.3, if 2 lines intersect, then the intersection is exactly 1 point. Okay? If you intersect, you only intersect 1 time. Whereas up here, these intersect, those can intersect multiple times. Postulate 2.4, through any 3 non-collinear points, there's exactly 1 plane. Now, we've already talked about this. If you have 3 non-collinear points, you get a flat surface, a plane. A plane contains at least 3 non-collinear points. These are connected. They are converses. This says 3 points imply a plane, and this one says a plane implies 3 points. 2.6, if 2 points lie in a plane, then the line containing them lies in the plane. If you have a plane, and you've got a point and a point that's in the plane, then that line has to lie in the plane as well. If the points are in the plane, then the line is in the plane. The line cannot, somehow go off the plane. Next, if 2 planes intersect, the intersection is a line. Here you can see a picture of plane L intersecting plane K, and they make a line where they intersect. Now, we've already talked about this stuff. You've already been tested on it. So we're just making it a system right now. Okay, so a proof is an argument. It's an argument that uses statements that are supported by other statements that are true. So in this example, this is a proof. This statement right here was supported by these 2 statements. And this statement right here was supported by this statement. And this final statement right here was putting this and this together. That is a proof. It's like a puzzle, is what it is. Now, for reasons, a theorem is a statement that has been proven. That's what a theorem is. The reasons you can use in a proof are postulates. So those are just accepted as truth. Theorems, those have been proven to be true. Definitions, that's how we define things. And properties, those will be part of algebra. We'll see that. All right, so the next example, it says, state the reason for the statement if it is true. Okay, so for the first one, I'll give you an example. Is it true that planes L and plane K intersect at line PS? So here's plane L, here's plane K, and there's the intersection, and it is line SP. And if we go and we can reference theorem 2.7, which says, if 2 planes intersect, then their intersection is a line. So we can back up this true statement using theorem 2.7. Next one. U, M, and O are coplanar. So we have U, M, and O. U, M, and O. Are they coplanar? Well, according to 2.4, through any 3 non-collinear points, there is 1 plane. So yes, we do have 3 non-collinear points. That means we do have a plane. There could be a spider web, sure. And that's supported by theorem 2.4. Can you do the rest? Pause the video and try the rest. And now you're back. They're all true. This one's a little tricky. Can we assume that angle QOP is a right angle? And the answer is yes, because there's that right angle mark right there. It's hard to see, but yes, we can assume it's a right angle because that's the definition of that symbol. If we see that symbol, we know that it's a right angle. So that wasn't one of the postulates, but I threw that in there. Next, can we say for certain that this line here is in this plane? Remember, planes will extend forever. Okay, so this plane goes on forever. So M is in the plane K, Q is in plane K. So therefore, theorem 2.6, if 2 points are in the plane, then the line containing them is in the plane. So that one's good. And then lastly, the two lines intersect at point O. Yeah, the two lines intersect at point O. If two lines intersect, then their intersection is exactly 1 point. So yes, they intersect. And that was the lesson. Now you have to go to the homework worksheet and watch that video.